Welcome to another Fibre Laser Learning Lab. Today's session is entitled The End of the Rainbow because I'm going to be quite brutal and we're going to close the session on colour marking of stainless steel today. Now I hope it's going to be quite informative because I've been working laboriously for the past few days putting hundreds of samples through this machine, trying to zoom in on some colours that satisfy one of the grades that we talked about last time in my colour grading system. Now later on we should be looking at these colours under the microscope because it is very important that you understand where and how these colours come about and some of the, I suspect, untried, new and tested methods that I have exploited to try and get these colours into a position where they are durable and fast to produce. That most of the colours that you have seen to date, mainly in the D category of my listing. Now I've got a few of those here, and what I'm going to do initially is to just show you the difference between A, B, C and D grade colours. Now we're very fortunate today that despite it being a cold day, it's a lovely sunny day outside and we should be able to step out into the sunshine and look at the durability of these colours in natural bright sunlight. I've also got beside me here some LED white lights. Although I could use fluorescent as well, I think these three main variations of light will demonstrate the point that I'm going to make. I hope you can forgive the lawnmower in the background. My neighbour's busy cutting his grass. Very fortunately, I don't have any grass because my dad was a bit of a philosopher and he told me when I was younger, never have any more grass than your wife will mow. Now I've had a slight change of plan because I think it's of benefit to pass on, if possible, some of the experience that I've gained over the past few days of playing with all these parameters. It's given me a tremendous insight into just the huge variety of opportunities you've got on this machine for controlling the power down onto the surface of the material. Colours is all about heat per unit area, and you can change the heat per unit area in so many different ways with this machine. Anybody getting one of these machines for the first time is likely to be extremely confused by all these parameters, much the same as I was. With practice, I've managed to begin to understand the relative importance of some of these factors. Now, this is a MOPA laser machine. Now, one of the most confusing things about this machine is all the pulse types. We've got pulses that are 2 nanoseconds long, and we've got pulses that are 350 nanoseconds long. Now, you achieve these pulses by running the machine at these specific frequencies. Now, 850 kilohertz is, let's just call that 1,000. 1,000 kilohertz is 1,000,000 cycles a second. So that means every cycle equals 1 microsecond. Now over here, we've got 350 nanosecond pulse, but you achieve that at 25 kilohertz. And that means a frequency of 40 microseconds. So it's 40 times slower than this. But the pulse is 350 nanoseconds. This pulse is 2 nanoseconds. So in terms of pulse duration, this one is effectively about 170 times longer than that one. So this pulse here is 170 times, roughly 170 times more than that one in terms of duration, but its repetition rate, the number of times that that pulse gets put down, is 40 times slower. And this is the strange balancing act. What I'm first going to do is just quickly show you in a sample patch the difference between these two. So you just get a feeling for the damage that these two extremes can do to the material. And there we go. That was a 2 nanosecond pulse. Did it do much damage? So yes, it did a little bit of damage to the surface, as you can see, But I'm going to use this as a classic example of something else that I'm going to talk about in a minute, which is the light sensitivity of the pattern that we've produced. Now look, I'm going to rotate this very slightly backwards and forwards, and as I rotate it backwards, it turns to black, and as I rotate it forward, I get the pattern back again, and then it turns to black. It's got a very narrow viewing angle, and that viewing angle is less than plus or minus 10 degrees. So I'm now going to go to the other extreme, and I'm going to put a 350 nanosecond pulse in, and we'll do exactly the same test. That's all I'm going to change is the pulse size. I think you can see the difference in the power there. You can hear it and you can see it. That is a pretty powerful pulse. I'm using 100% power. I'm using 2000 millimeters a second for doing all this work, and we've also got a line spacing of 100 microns. There's our first one. If we hold it into the light just right, we can see that there's not a lot of difference in the colour. They're both silvery white, and if I start rotating them, look, the first one disappears and goes to black, and the next one, well, that can go a long way, look, and it still remains white. So one of the main advantages of this longer pulse is we get a more durable mark on the surface. We're not just tickling the surface, we're damaging the surface. There's a lot more complexity in these numbers to be analysed when we get onto another section. But I just wanted to show you the difference between these two pulse types to start with. Now, percent power is quite a complex factor. It's not just a simple matter of saying, well, when I get 100% power, I shall get X amount, and when I put 50% power down, I'm going to get 50% of the effect. It's not that simple, I'm afraid. So something we talked about quite a lot when we spoke about focus was the shape of the energy, the intensity of the light within the beam. The beam goes down to a focus point like this, and at this point out here, up from the focus, we've got a certain amount of power. Let's call it 20 watts. It doesn't really matter, but there's a fixed amount of power taking place there, and that power is spread in a Gaussian fashion across the beam. And let's say it looks like this. Well, if we squash the beam down to a smaller dimension, we've got the same amount of power under the beam. And effectively what it does, it causes the beam profile to do this. It squashes it up. Now, I've drawn it upwards because that's the way you normally see a graph, but in reality we also got to be looking at it this way round and saying, well, our beam profile looks like that. The intensity of this light is not uniform across the beam, and as we move further and further away from the focal point, although you would normally expect the beam to get weaker, in fact it doesn't get weaker at all. Depending on the amount of power that you put into the beam, you could have this power 10, 15 millimeters below the focal point that you can do damage with. That is effectively what 100% power looks like. It's a sharp pencil. That's the best way that I can describe it to you. It's like writing with a very sharp pencil. When you reduce the power to 20%, you're doing effectively the same as this. So you're making it very much a smoother distribution at the focal point. I know it's a silly analogy, but it's probably something that will stick in your mind. We've got a sharp pencil at 100% and a blunt pencil at 20%. So there are many different ways of reducing the power into the surface, but one of them is probably not percent power if you want a sharp, crisp image. If you want a soft, gentle application of heat, then you reduce the percent power. Let me try and prove that to you. Did you see it? That was what 20% power was. If you look extremely hard with a little bit of imagination, you might be able to just see something. There it is. Look, look, look. We catch it in the light just right, and we can see some surface marking. So what we've just seen there is two effects. Not only have we got a long pulse, which is effectively a soft, blunt pulse I would like to imagine it as, because it's not a sharp, crisp pulse like this one. So we've just blunted this blunt pulse with a blunt pencil. And that means we're not putting very much power down onto the surface at all. We're not damaging the surface very much at all. Now, my analogies are very crude, but they are images that I'm carrying in my mind and have helped me to understand the relationship between these very complex factors. Okay, so we've got our blunt and sharp pencil analog for power. So my images for this range of pulses, it runs from delicate and sharp to, if you like, brutal and blunt. That is like a scalpel, and that is like a lumberjack's axe. You wouldn't perform brain surgery with that, but you might perform brain surgery with that. It's a scalpel and an axe, as we said. Now, there is a serious interplay between these numbers here, the frequency at which the repetition frequency at which these pulses occur, and the linear speed. Now, before we jump onto speed, which has a direct relationship to this, there's something else you need to understand about these shapes, and I'm going to use this one as a good example. As we said, this is roughly 1 microsecond. Okay, a millionth of a second. But this pulse is only 2 nanoseconds long. A nanosecond is 1,000th of this division. So just here, where my line is that pulse. And we travel for a whole microsecond, a millionth of a second, before we get another pulse. And then another millionth of a second before we get the next pulse. So there is a huge space relative to the pulse size in between the pulses to the next pulse. So if you like, that is heat, and that is cooling. So we put a little teeny weeny spike of heat in, and we have a huge amount of time over which it gets a chance to cool. How on earth are we ever going to get any heat into this product? Well, the answer is really because of the thermal reactivity of the material itself. The material cannot cool this quickly. It can heat up, and eventually, if you heat it enough times in the same spot, it will get hotter and hotter and hotter because it does not get a chance to cool in between the pulses. Now, that's an important fact to remember, that if we can put more heat into the same spot, we will gradually raise the temperature of that spot. Now we come back to speed. So when we look at my chart of the various frequencies and pulse lengths, you'll find that across the bottom here we've got a ratio which is 588, 500, 500, 435. They're all in the 4 to 600 to 1 ratio. Okay, so we've got a very long cooling period for a very short heating period, regardless of the pulse. So with our 2 nanosecond pulse at 2000 millimeters a second, even though we're running at 850 kilohertz, which is nearly 1,000,000 times a second, we're only putting down 425 pulses per millimeter. If we reduce the speed to 1000 millimeters a second, we double it, 850, which means we're putting twice as much power into the same millimeter of stroke. So the slower the speed, the more pulses we can get. I mean, down at 100 millimeters a second, we get 8,500 pulses per millimeter. If we were to drop it down to 1 millimeter a second, we'd have nearly 1,000,000 pulses. We'd have 850,000 pulses per millimeter. There is a very interesting relationship there, and an important relationship between speed and this frequency. And that's what this table attempts to show. So we can effectively increase the power and the effectiveness of this pulse by decreasing the speed at which we apply them. Because as we slow the speed, we get more pulses per millimeter. and that means we're going to do more damage by running slower. Here's the first one that you can't see, which is 2000 millimeters a second with a 2 nanosecond pulse. Okay, so now we've reduced the speed to 500. So it's a quarter of what it was before at 2000. You can actually see the scan speed this time. Now, two things I hope you'll notice. First of all, we've got some colour in there now, look. This one is a quarter of the speed of that one. So there it was silver, and now you're getting a hint of colour in it. Because what we've done, we've increased the power, and we're actually burning effectively the metal. We're producing a yellow oxide film on the surface. In terms of light sensitivity, about the same. Look, they're just about responding the same. And then if I tip it the other way from the light, no, they're both disappearing at about the same time. And here's my chart for the 350 nanosecond pulse. We're only running at 25 kilohertz, remember. So therefore the repetition rate is very, very slow. So we're only getting 13 pulses per millimetre at 2000. But look, we did this amount of damage with just 13 pulses per millimetre. If I reduce it to 500, I'm now going to put 50 pulses per millimetre in. So I don't think it takes a genius to realise that we're going to put a lot more power into the surface and we're going to do a lot more damage. You should both see it and hear it. Now we've turned it into a very dark gold because we've put a huge amount more heat into the surface. What have we done to the light durability? It was pretty good before. That's extremely durable as far as angle of light is concerned. As I said, this has been a fascinating insight into learning about the machine, hunting for these colours and understanding the way in which the parameters work. So we've seen the way that speed, linear speed, can affect the amount of power that we put down in the horizontal direction. If we want to change the power in the vertical direction, we have the opportunity to do that as well. If we're doing engraving, which we are most of the time because this is a scanning engraving machine, then what we have the opportunity to do is to play with the line spacing this way, the pitch between the lines. Now at the moment on this test patch I'm using 100 micron spacing. I've got a 60 micron beam on here, and so effectively there's dead space between the lines that you're looking at on this pattern here. You can't see that because your eye is just not capable of looking at that resolution. We shall see it under the microscope, but not with your eye. Let's forget that mistake that I made there. In this horizontal direction with that one, we increased the power to the surface by approximately a factor of 4 in the horizontal direction. So what I'm now going to do is I'm going to modify this one by changing the line spacing from 100 microns to 25 microns, which again has a ratio of about 4:1. So we should find that we come out with more or less the same colour as this one, because we've got the same amount of power going down per square millimetre. So I think that demonstrates to you clearly that changing the power ratio in one direction is not exactly the same as changing the power ratio in the other direction. There are differences. We get more effective heat change by horizontal change than we do by vertical change. And that's an important lesson that I learnt when I was hunting for these colours. So these very coarse, glittery colours, as you can see, are much more resistant to light change. Now, the final factor, which sometimes has very little effect, is the hatch pattern. So these are the important factors. Just here, we've got this little pattern. We got the opportunity to change this type of hatching. Let's just go from the start. The red lines are the flyback and the blue lines are the actual cut. So in this particular instance we've got a cut which is always in that direction. Okay, it's called a unidirectional cut. we have the opportunity here of a bi-directional cut. You'll see there's got red lines at the end, which means that we're not cutting, and so we're cutting in that direction and that direction. That's bi-directional scanning. Then we've got this really strange pattern here, which I don't know what the value of it is, but hey, it's there if you need it. I've found that that's of no value to you for producing colours, because you get tremendous change in the energy density as you work towards the centre of the pattern, the heating effect. These are things you'll have to find out for yourself. But the critical one, which is very useful, once you've got one of these patterns selected, and let's choose that one, which is the bidirectional scanning, which is slightly faster than the unidirectional scanning, but it's negligible. Is this thing here. If we tick this box here, crosshatch, what that will do a series of lines like that, and then it'll do a series of lines like that. And that's a very useful pattern which I've discovered for producing colour. Now, in the last session I spoke about my colour grading scheme, which I was going to use to judge the success or failure of each one of the patches that I was making. And I've refined it quite a lot since the last session. And so what I'm saying here now is my A grade, I need a very wide viewing angle, greater than plus or minus 60 degrees. And that's with all light sources. Now, today we're likely to be checking it with a halogen light, an LED light and daylight. So that's a pretty reasonable mix. I have got fluorescent light in here, but fluorescents are so many different colours that, you know, we're going to discount those at the moment, and we just go with the three main sources of light that you're likely to find these being exposed to. Now, colour fidelity is whether the colour remains the same for all light sources. For instance, LED light has got a very narrow spectral range, whereas daylight is wide and halogen light is a close approximation to daylight. So we're likely to see significant colour change with LED lights. A very important factor for me really decides whether these colours are good or bad is whether they can be put down quickly. I mean, this is not untypical of the sort of size image that you might want to work on. I had to give up on this mauve image after about half an hour because that's as far as it had got. Well, here the gold and the white or latte colour, we've got 1 minute 25 and 1 minute 48. Now they're completely acceptable production times for an object that size. All my little test squares have been rationalised to 1 square centimetre. Now, regardless of whether that's got any engraving in it or not, 1 square centimetre is 1 square centimetre. If you want to work out how long it's going to take for this image to do, you're just going to have to put a little average rectangle around it and work out how many square centimetres are in there. So this image, for example, is on average, let's just have a quick assessment, a little bit in, a little bit out. So that's roughly 6 centimetres. 6 centimetres by about 5, 6 is 30 square centimetres. So if it takes 5 seconds per square centimetre, and we've got 30 of them, that's going to take about just over 2 minutes. So that's just one colour. I've now got to add the area for each one of these other colours that I choose to put in here as well. So by the time I've filled in all these here, that could take 5 or 6 minutes to do. Is that acceptable? Could I charge out at a rate which would allow me to get a good recovery on this machine? That's a decision that you will have to take, but it all depends on the speed of which you can put the colours down. That's productionising these colours so that they become useful. So the factors for the other grades are similar, but for instance a B grade, instead of plus or minus 60 degrees, I've nominally chosen plus or minus 30 degrees based on my experience. It's very likely that they could be as much as plus or minus 60 degrees. They could be A grade viewing, but they could be incredibly long as far as production time is concerned, which throws them out of the A grade and puts them into a B grade where you may want to use them. It's up to your judgment as to whether or not it's cost effective. C grade and D grade, very similar, except that C grade have got a little bit more viewing capability than a D grade, which is very limited at about plus or minus 10 degrees. And to be honest, most of the colours that you're going to encounter from other manufacturers who tout the colour chart as, you know, the best thing since sliced bread, it's not that good, because, you know, I wouldn't buy a machine based on something that I would class as D-grade colours. I'll now use a few examples to look at these various gradings. The gold on the end has turned orange. The Kingfisher blues in the middle are more green. That mauve is not bad. So that's holding its colour, but because look, I've only got to turn it by a very small amount of angle and it all changes. Now that's quite a nice orange on the end, isn't it? I thought that was a gold. But here, in sunlight, it's definitely orange. Very quickly you can see how easily they're all black now, almost, except for the gold one. Now let's just rotate them around very, very gently. Look at the colour coming in, and then all the colour disappearing. That's why I call those rubbish. I mean, there's our B-grade colours. And let's rotate them round. And there's quite a few of those that you can see are pretty robust. They're a long way rotated. And these have got quite a wide viewing angle. So we take a look at these in white light, LED light. We can see the chameleon colour on the end there, which is a mauve come gold come. So they're moderately robust, those colours, but the problem is time. Now in white light, I mean, these colours don't look very much different than what they do in daylight. Sadly, that's it. That's your colour palette. Very, very limited. Browns, silvers, golds, a black, pink and a mauve. So don't get excited. To confirm my conclusions about colours, on stainless steel at least, I'm going to run this little program in real time for you. So settle down with a cup of coffee and off we go. Okay, so that took about 4.5 minutes. And you can see my colours are pretty good. They don't change as I move it around. And this is in white light. Let's go and have a look at it in daylight. See if we can get some sun onto it. There we go, we're now in nice sunlight. Well, since I selected my colour palette originally, my A-grade colour palette, I've been a bit more brutal with it, and I've reduced it down to probably only about 8 or 10 drab colours. Well, I say drab. You've got some golds, you've got some coppers, some grey, come green. Yeah, I mean, there's a reasonable range there, but it's nothing like what you're being sold. As you saw when this was being produced, silver, that silver around the outside, that whitey silver, is a nice rapid colour to produce. And you could use that on stainless steel, it shows up very well, as you can see. And gold as well also shows up well. But apart from those two main colours, I can't see that you need many more for engraving text on something. Well, we're going to start looking at the D-grade colours. Now, this is, I think without any surprise, a gold. That's 50 times magnification, and this is 400 times. No surprises there. Hints of green, but mainly yellows and reds. Net result, you get what you see on the screen. There's no variation in depth. So let's take a look at the next one. A bit of a sky blue. Again, as I fiddle with the focus, the colour is just in the film itself, in the oxide film on the surface. Next one is Kingfisher blue. Slightly different patternation. No, everything's at one depth there. I can just fiddle with the focus, but nothing changes focus as I go up and down by 1 or 2 microns even. Now this came out as a salmon pink, and sure enough, I think you get what you see on the screen. It's a mixture of yellows and pinks, but the predominant colour when you look at it is salmon pink. I think we've more or less seen that pattern before in another blue. It's difficult to say where the focus is. I think the focus is just about there. So that's the dark maroon colour, but again it's flat. Run over it with the laser again twice and you get what you see, which is blue. Okay, so that's a quick look at the C and D grade colours, which we're not really interested in. Well, I'm not interested in it, let me be fair about it. What we're going to look at now is really my A grade colours. Now the great thing about this colour chase that I've been on is that there seemed to be so much that people have not discovered about these colours. Or if they have discovered them, they decided they're not worth pursuing or they're rubbish. The work that I've done has allowed me to discover 3 different basic types of colour. When I say types, I mean textures. You've now seen those that I disparagingly call D grades. They are basically the principle of thin film interference, which people have discovered to the nth degree. The colours that I'm interested in, still using the thin film interference principle, but looked at in a completely different way. What you see on the screen there looks like, I don't know, a piece of pink gravel. Well, that's exactly almost what it is. It's a disrupted surface which causes the light to change in so many different directions. The thin film that's on that surface cannot be pink. There is no pink oxidation colour. So the only reason we've got pink is because there is already a mix of white light coming out to the microscope before it even reaches our eyes. Now look at the amount of black in there. There is no indication of black when we look at that with the naked eye. We only see a predominance of pink. So that's a gravel effect, and we can look at that. That's looking at it at 50 times magnification. If we just bump that up to 400 and take a look at it, now I can't get it in focus because there's so much change of focal depth. Let's come in and raise the table up. So we pick the high spots up first in focus. And here we go. Look, we've got some high spots here coming into focus. And now we'll go up a little bit more. And now we've got the stripes at the bottom of the valleys. Okay, so that's a three-dimensional pattern. You've got two forms of colour mixing on that surface. Now the first form of light that you're seeing there is from the tungsten lighting in the microscope. You've got thin film interference off the surface, which is creating the different colours, yellows, pinks and blues. The flat surface at the bottom, that lovely canary yellow, that lovely pink, they're not in the colour tempering range. The only reason we can see them is because we've got an interference pattern which is affecting the light before it even hits our eyes. That's what hits the microscope. But the time it hits our eyes, all those colours are agglomerated and further interfered with, and our eyes only see, and the best I can show you is that. That's 50 times magnification. By the time we see it, it's 1 times magnification. This surface is totally unpredictable in a strange sort of way. It's chaos. Here we're getting variation in the thickness of the film superimposed on variation that we've caused to the surface of the material. So we've got ripples here like you see on the sand when the tide goes out. That's the second type of interference pattern that we're perceiving with our eye. There is a third one which I'm not sure that anybody has ever explored before, and that's something that I accidentally came across and revealed to you at the end of the last session. Now I've pursued this quite intensively because this is where the A-grade colours really exist. This, as far as I'm aware, is not something that people have ever been doing before to get colour on stainless steel. That is a gold. Where is the gold colour coming from? Well, it's coming from the surface of these little squares. Now this is not an area of science that I've seen anybody else working on, discovering, using, exploiting. What you're seeing here is, to the naked eye, a lovely glittery gold. What we've got here is a 60 micron beam. And what we've got here is a 200 micron spacing. And in between that grid, we've created a heating effect on the surface. Now, if you look at the colour of each one of those squares, you'll see that what we've actually done, we've created a flat, thin film interference pattern on each one of those. We've created a colour, which is pink, yellowy, whatever it is, it hits the eye as a sparkly gold. And it's viewable from all sorts of directions. And I think that's purely because we've exploited the principle that we started off thinking about, which is a cellular structure. Although they're nanocell structures on a butterfly wing, these are bigger, but they're exploiting the same effect. We could go and look at that a little bit closer, a lot closer at 400 mag. As I raise this image up and bring it into focus, look at the black lines around the edge of the square. That's the debris on the side of the beam. Now I'll carry on raising the focus up and you'll see the surface come into focus. And then I'll raise it up more and you'll see the beam groove then coming into focus there. So there's a lot of depth in that picture. Now that's not an incredibly powerful beam. It's one of the power beams. It's 100 nanosecond pulse. So it's in the fairly powerful region, but it's not certainly one of the most powerful beams. In fact, I'll tell you what, let's go and look at a powerful beam now. This is silver, 400. We've got 2000 millimeters a second speed, and yet we're only running at 25 kilohertz frequency. So what you're able to see here is individual pulses. And look at the metal that's splashed up around each one of these pulses.
as soon as the liquid stainless steel hardens, and it must have been liquid to produce these blobs, we get a film, an oxide film, that is created on the surface. As I mentioned to you probably in an earlier session, from all the reading that I've done, this oxide film forms within a few nanoseconds of the metal being exposed to oxygen. So there will always be a film of some sort on the surface of stainless steel because of the interaction of chromium and oxygen. And that effectively is freezing the colour into the surface. We've got the melted surface at the bottom of the beam, and we've also got that surface there, which is an undisturbed surface of the base material that has not been cut or melted. And what you're seeing there is the heating effect of the beam all around that little flat section. It has caused its own thin film interference pattern of orange. So that is a flat film interference pattern, and the others are some three-dimensional pattern. There is no green in the natural oxide colours. So the only way that you can get green is by an interference pattern. But of course, those cauliflower shapes, as I described them, are not sticking up. They're little pits. So you've got reflection off the inside of each one of those pits, which is doing strange things to the interference patterns of light coming off that surface. And by the time it reaches your eye, it looks like silver, glittery silver. Now that I'm moving into this sort of technology, this is not predictable. This is total chaos. So there is little or no predictability to the colour that I'm going to get. It depends on the damage that I do to the surface and the heat that I put into the surface and the heat that I'm leaving behind in this residual undamaged area. So let's take a quick look at a few more of these colours. So I'll drop the magnification down to 200 so that we can see things quite quickly. I'm just zooming in and out, I'm just moving the focus around just so that you get an idea of the fact that there is quite a lot of variation in the depth of these things. That's a sort of a latte colour, very light fawn. It's on the edge of a glittery gold, but it's a little bit less than a gold. Now isn't that beautiful? Now that's a mid gold. It's quite a light, bright gold, but you've got colour in the beam as well there. That's an 8 nanosecond beam. So we're not doing as much damage with the beam itself, and that's why we can't see the striations in the bottom of the beam, because these are running at 250 kilohertz. And we're running the whole thing at 600 millimeters, which is quite slow, relatively speaking. But look, here we've got enough heat to produce blue round the edge of our square. So that's one of the very fast golds that I can produce. Takes about 2.9 or 3 seconds per square centimetre. So this is exactly the same settings as the previous one, except the speed has been changed from 600 to 400. So in going down to 400, we've actually allowed more pulses per millimetre, and we've had a greater heating effect. So our gold has now changed into a copper colour. And maybe you can see that in the redness of the beam. And that's what's probably causing the effect when it gets to the eye. I absolutely love this one. This is like almost a modern artwork. This actually comes out as a very, very dark gold, almost a brown. Now here's another lovely silver. And if you remember, it's not dissimilar to the silver that we first saw, because this again looks like a field of cauliflowers. I mean, this again is done with a maximum power beam, 350 nanosecond beam, but it's running very slowly at 25 kilohertz. But we're also running at quite a high speed, 1000 millimeters a second, which is why you can see the spacing between the pulses. So we've still got gold squares in there, but we get no hint of gold when it meets our eye. All we see is silver, despite there being a lot of green in there and not much white. Now here we've got something that's completely different. To the eye, this comes out as a smooth gold. Although this is very fast to produce at 9.5 seconds, it is not entirely durable as far as the viewing angle is concerned. So I think I demoted this to a B grade. Now you've seen this before, because this is a silver. In fact, I have to say that to the eye, this looks very white as opposed to silver. Should it? Does it look white? Not really. So between physics and your brain, there's something weird going on. Okay, any guesses as to what that might be? In most lights, this looks like a dark grey, and it's the dark grey that I used on the butterfly wing. In other lights, it's got a little hint of brown in it. This is definitely an iridescent colour. And yet, can you see any hint of grey on that picture, or any hint of brown? As I said to you earlier, this is chaos in action. Now, most of the others, as you have seen, have been crosshatch pattern. Now this one isn't a crosshatch pattern, and it produces a matte finish. Any guesses to what the colour might be? Jet black. No, it's not a dark gold. That again is something you see on the butterfly wing. So that's enough of colours. I think I've done enough research. I think I've done enough discovery to set you guys on a trail if you wish to follow any of these directions and look for colours for yourself. There are some new avenues here which I'm fairly confident have not been discovered before. Now the other interesting thought is for those guys with a Q-switch laser. Looking at the very high powers and slow speeds and relatively low frequencies of some of these settings, it is very possible that you might be able to use this technique to find colours on a Q-switch laser. I haven't got a Q-switch laser, so I can't experiment with it. So I'm going to leave this problem with you now. I am not a user of this machine. Bear in mind, I only play with this machine. I get tremendous enjoyment from this machine, and what you do with it is up to you. So I think that's a very convenient place to stop at this moment in time and say thank you very much for your patience, and I'll catch up with you in the next session where we will, I promise, not be touching colours.